ocean waves or something, okay? And imagine a large number of corks on the shore. And I want to move corks in a small space. And the only waves I'm allowed to use are this long. It's impossible to figure out how to get waves at this normal wavelength to focus any shorter than about this size. You can, by bringing the waves from different sizes from a much bigger dimension, bring things in, focusing the waves, but you can't get them any shorter than this characteristic length of the waves. And so the sloshing on the shore will move corks over about this much area. It's impossible to pick one cork out with waves that are this long, no matter how you combine them, okay?
How do you combine them?
Well, by taking different waves, yes, indeed.
Because
now, but different waves are not called light. We call them ultraviolet light, or X-rays, for instance. X-rays are, in fact, exactly that. They're light, but with a shorter wavelength than normal light. Now, in principle, you could do, and people are trying to do, this kind of a thing in which the X-rays affect the resist. You're absolutely right. They have to go through all the technique. The photographic technique for making the pictures can't be silver and so forth, but you do it a different way. And there's a lot of work. And X-rays is, in fact, one way that is being worked on in various laboratories to reduce the size of this. Yes, that's a good idea. I'm sorry I answered your question wrong before, saying there was a limitation because of light. I was assuming it was light. Yeah, but it could be X-rays. Or ultraviolet light. That's going a little bit. Ultraviolet light about half size, okay? But beyond that, we call it super hot, far ultraviolet or X-rays. Then there's soft X-rays, hard X-rays, so on. The size is going down and down and down. And that size can get smaller than an atom. It can get way much, much smaller, the size of a nucleus. I mean, it's hard gamma rays and so on. It's all the same scale. But the other direction in scale of a longer wave is called red light, infrared light, far infrared light, heat waves, radio wave, or television transmission waves, and radio waves. There's all one enormous scale from one end to the other, which from a physics point of view properly is the same thing and should be called by the same name. If we call it light, you may get a mistake because you think you mean visible light, okay? We call it electromagnetic radiation, which is a great big word, but it's supposed to encompass this phenomenon, which can have a scale like the ocean waves. But depending on what the scale is, the normal name of the thing is different. It's radio waves, or one day...
harmonic.
Yes, a harmonic oscillation, slow for radio waves, faster for television waves, faster for heat waves, faster for... and very fast for red light, and even faster for blue light, and then ultraviolet, and so on. It's just the same damn thing along a whole scale from one enormous range. Okay? Yeah.
I'm confused about...
Again? I have such trouble with you. You're always confused.
How can you detect something that's smaller than atoms? What can we have to detect them with?
That takes a great deal of ingenuity. Now, let me explain to you how you might be able to do that. Suppose that you wanted to detect something smaller than tennis balls, and all you have is tennis balls. Okay? Now, if you hit a tennis ball against a tennis ball, it's unlikely to bounce directly back. Well, excuse me, that's too complicated. Suppose you throw tennis balls at a wall of these things that you want to test if they're smaller. Then by seeing that how many tennis balls come through and how many bounce back, you can see how big the targets are. If one tennis ball has to occupy an area size of a tennis ball. So if you had one tennis ball on the wall and you threw them at random at it, the number that would bounce back would be depending on the size of that ball. But if that wasn't a ball but a pin, you'd have to have better aim. Yeah, something like that. It's something like that. So we measure, that's one way of going down in size. Okay? Another way of going down in size is to discover some relationships. For example, one of the ways of making light is to let electrons hit something with a certain energy, hit a metal. As you increase the energy, when you can still measure this wavelength, because it's still bigger than an atom, you measure it and you find the wavelengths getting shorter as you increase the energy of the collision. Now, you get to a point where you can't measure directly anymore, but the the way you understand the laws is you just use more energy, you'll get shorter wavelengths. And that's the way we go to very much shorter wavelengths. And then after we make measurements, everything fits together, and there's lots of internal checks and so on. It's not very easy to describe in a few words.
Smaller than an atom, not smaller than an electron. I guess.
Yes, smaller than, well, it's hard to say how big an electron is, but it'll be pretty damn much smaller than an atom in the following sense. An atom, say, is the size of the room, okay? Then the nucleus of the atom is a tiny speck. It takes me a minute. 100,000th times smaller. 100,000 times smaller. So you have to think exactly. It's a little tiny dot, like a period in a sentence, which is much smaller. And that we can measure too. But today we have, by using this method of using high energy collisions, with the high energy corresponds to short wavelength, we can go down to 1,000th of the size of a nucleus, of the smallest nucleus. So we're down on the insides of protons and things at the moment. That's what your taxpayer money has been able to produce. Yes, ma'am?
Can you use sound the way you use light? Could those little arrows be sound?
They could in principle, but sound wavelengths are very long on the scale. These little things, and the distances I'm drawing there are millionths of an inch.
But are there new kinds of sound, like
Ultrasound.
and could you do
Ultrasound.
the same sort of...
Yes, ultrasound is smaller and shorter, and you could, indeed you're right, yes, you could use this very super frequency sound, not ordinary sound, not sounds you can hear with the ear.
No, I don't... Yeah.
Supersonic. No, not
Pictures
supersonic.
is...
Yes, you're right, I made a mistake. I'm sorry, yes. Not auditory sound, but you could do this with short-range sound.
I mean, is there any...
It's so easy with the light, and to get at these small distances, it's rather difficult with the sound, because the sound is a wave in matter of motion. And the matter is disorganized, the matter is shaking all the time, and it's hard to keep organized waves going any distance.